As we are now basically at the end of our Introduction to Integrals chapter, one of the hardest things that we're going to deal with, and I mean it's going to be hard on your AP tests and just in general with integrals, again, which are harder than derivatives, is that things are going to start looking all kind of similar, and there's not just going to be one way to do these problems. Take a look at the first two problems in our 5.8b practice stuff. Almost identical. This power is different, and it's actually going to drastically change how we do this problem. We got to think about all the things that we currently know that are going to help us integrate. These don't look like basic functions that we're just supposed to know the antiderivative of. We might be able to use U substitution. We might be able to use some natural log ideas. Don't see any trig this time, but we always got to be on the lookout for those structures for our inverse trig functions. Let's look at this first one. What are some ideas? What are some things that I'm thinking of? Well, I noticed that we have some square stuff on the bottom. One thing that I'm thinking, 4 is 2 squared. 9x squared is 3x squared. So maybe this is like an arctangent thing. But I think the problem we run into if we're thinking arctangent is that if I make my u is 3x, then my du doesn't have an x to replace. And we have this 5x on top that we also would need to replace. So with that in mind, I don't know if arctangent stuff is going to help us this time around for this one. So maybe what's another thought to have? This is quadratic, and when I take the derivative of quadratics, I get linear stuff. So maybe I'm just going to try a straight substitution for this one. Let's see how it goes. What if u equals 4 plus 9x squared? Taking the derivative, du is going to equal 18x dx, and that x right there makes it kind of look like, yeah, this might be the way to go. Because I can replace that x dx with a du. I'm actually going to divide by 18, so I'm going to actually replace x dx with 1/18 du. So let's rewrite our integral. I'm going to put the 1 over 18 out front. I'm going to put the du at the back, so everything I highlighted will go away. That 5 on top, I actually probably just want to move out to the front as well, just to make it easier on myself and see it. That'll leave us 1 in the numerator. In the bottom, I'm calling u. Now the integral doesn't look too bad. Got a lot of practice with this section or two ago. That is 5/18 natural log, the absolute value of u plus c, which, if we write back in our x variable, it's 5/18 natural log, the absolute value of 4 plus 9x squared plus c. A quick note here. If you didn't write the absolute values this time, just had parentheses, that's okay. That works. Why? 4 plus 9x squared, always positive. So you don't actually need the absolute values for something that's always positive, no matter what you plug in for x. If you write them, it's not a big deal, but I just wanted to put a note there because sometimes if you're like checking your answer or anything, you might not see the absolute values and you might think, why didn't we have to write it that time? Normally it's because the thing inside the natural log can't be negative if you didn't have the absolute values. Anyways, moving on. Having just done u substitution, you might think, well, probably not going to be u substitution for this next problem, but let's verify why. Maybe you try to take the denominator and make it u again. But when you take the derivative this time, derivative of 4 is 0. Derivative of 9x to the fourth is 36 x cubed dx. And we certainly don't have an x cubed to help us replace our dx with du stuff. So I'm going to say it's probably not u sub. So what else are we kind of thinking right now? There's no trig. This is not a function that I just know the antiderivative off the top of my head. Looks kind of tricky. Maybe now I'm thinking, I kind of see that 4 is 2 squared. The 9x to the 4th, that's 3x squared squared. Maybe this is one of our arctangent problems. Let's try it out. Integral 5x over 2 squared plus 3x squared squared dx. If I call this 3x squared u, then du will be 6x dx, and that takes care of our x dx problem right there. It's going to let us get rid of that stuff, make this look more familiar. But I should definitely divide by 6 before getting too far ahead of myself. Let's bring the 1/6 out front, and let's also bring that 5 out to the front. So we have 5/6 out front, 1 over stuff, and I'll put the du at the back end, and then we have 2 squared plus u squared in the denominator. This, something we got to memorize, something we got to be comfortable with. That's going to give us arctangent. So we have 5/6. How do we do the arctangent thing? Remember, that's our a value. Our a value is 2. We need 1 over a times arctangent of u over a plus c. And then finally cleaning things up and replacing u with x. 5/6 times 1/2 is 5/12. Arctangent of, what is our u? Our u is 3x squared over 2 plus c. So again, kind of analyzing what's going on here. This is going to be the tricky part, is figuring out, looking at an integral, what's the best way to approach it. Sometimes you'll get to some dead ends and you'll have to try something else. It can be tricky, and it does matter. These powers, the things that you're trying to replace, u substitution, inverse trig stuff, got to be prepared for all of it. Looking at the next two problems, again, they kind of look similar. I see a -3, I see a 5. In this example on top, I see square roots of x. In the bottom, I just see plain old x's. So I don't know. They both kind of look like they might be some setups for some like arcsecant type answers. But arcsecant needs a u squared under the square root. And well, I guess we could make that work for the first one. It's written backwards, and again, that doesn't stop us from it being arcsecant, but because maybe it's written backwards right now, the variable thing isn't in front of the constant thing, maybe I'm not trying arcsecant type stuff for that first one. Maybe I should try u sub. What would be a good u substitution in this problem? Well, I guess we have this 5 minus square root of x inside of a square root. There's a composition of functions right there. Maybe let's try that out. U equals 5 minus square root of x. When we take the derivative, du is going to equal 0 minus 1 over 2 root x dx. Is this helpful? Actually, you know what? Yeah, I think this is pretty good. Got that negative right there, and we got the square root in the bottom. Got that negative right there. We got the square root in the bottom. I think u sub is probably looking like the way to go. I need to move this 2 over here to the other side. So 2 du equals -1 over the square root of x dx. Yeah, I think this is going to be pretty good. So everything that I highlighted gets replaced by 2 du. We have this 3 up top that I think I'm just going to move out to the front. Again, trying to make it easy on myself. So we have a 1 on top, and what do we have left on bottom? We have a square root. Don't forget the outer square root, but we're going to take the 5 minus square root of x and replace it with u. This looks like something we are able to do. So we have 6 integral of u to the negative 1/2 power. When we integrate, we add 1 to the exponent. So that's u to the half. We multiply by the reciprocal in front. That's 2. Can't forget our plus c. So that becomes 12. U to the 1/2, let's just write a square root of 5 minus the square root of x plus c. So that one is just a u substitution problem. Kind of gross, but still just a u substitution problem. You look at the other one, again, very similar. We don't have square roots of x, and the x being in front kind of makes me feel like I want to try to do arcsecant instead. What if you didn't think that and thought u substitution? Let's show why that's not going to be helpful. You would probably, I'm guessing probably, want to rewrite u equals x minus 5. So du would equal dx. And then you'd have this extra x floating right there. So you might say, well, if I rewrite the first equation, x would equal u plus 5. So what will we get? We would get negative 3 over u plus 5 times u to the 1/2 du, which would be integral negative 3 over u to the 3/2 plus 5u to the 1/2 du. If that stuff in the denominator was in the numerator, that wouldn't be too bad. We could definitely do that. But when you have a fraction where you have a sum or a difference in the bottom, recall you're not allowed to break up that fraction. You can't take a 1 over a plus b and write it as 1 over a plus 1 over b. It does not work that way. We can't break up fractions very easily when we have a sum or a difference in the denominator. And that's basically what makes this integral very, very hard to do this way, is that we wouldn't be able to rewrite here in an easy manner into something that we're comfortable with. So it kind of feels like at this point we're getting to a dead end if we try u substitution. So if u substitution isn't going to work, I'm going to try to make it look like a structure where I can get arcsecant as my answer. So if we need a u squared underneath our radical, I think I'm going to have to write it as the square root of x squared. And I think instead of 5, I'm going to have to write it as the square root of 5 squared. Because if we're going to try this the arcsecant way, it's got to have underneath the square root a u squared and a minus. Oh, I forgot to write a squared earlier. Sorry about that. At this point, we're going to say our u is the square root of x. So du is 1 over 2 root x dx. So how do these things play nicely? This is a little tricky. This might confuse you a little bit, but do your best to follow along. Instead of writing x out in front, what if I wrote it as the square root of x times the square root of x? Doing it this way, it might be a little bit easier to see that I'm replacing a square root of x in the denominator and a dx with 2 du. So the stuff that I have highlighted right here, I'm able to replace with 2 du. So let's start writing that out. I'm also going to take the negative 3 out front. Negative 3 times 2, integral 1 over. I'm replacing this highlighted one, but there's still the square root of x down there. Our square root of x right here I was calling u, so it's u squared minus root 5 squared du. And what do we do with this root x here? Well, we're calling the square root of x u. So actually, one more rewriting, negative 6 integral 1 over u square root u squared minus root 5 squared du. That is our structure to get our answer for an arcsecant of stuff.